We'll proceed in primitive calculus and we'll see vector aspect in calculus. If we see mathematics, then the beginning is numerical mathematics. On top of numerical mathematics, then we have algebra when we need variation. Means algebra which keeps variables. So when we need variation, then we have algebra. When we need computation on means collection and rate of collection, then we have calculus on top of algebra. When we need in algebraic equation, when we need direction and magnitude, direction, mainly direction, then we have on top of algebra, we have sitting is vector. When we need different interpretation as far as variable is concerned, then we have different coordinate systems. So vector that we will see in kind of where we can have interoperability with the calculus. Numeric science, algebra, calculus, vector, and on top of it different coordinate system. How how calculus and vector they interoperate. So that is something that we would like to see. Okay, meanwhile, we are in hurry to kind of to prove that circle circumference, the arc of the circle is perpendicular to the radius. So in that term only implicitly we will see the vector. We have seen gradient vector, single dimension. Now what is the equation of the circle? Equation of the circle is x square plus y square equal to a square. Okay, so equation of circle is x square plus y square equal to a square. Equation of the circle. If this is the circle, and this is x-axis, what is x square plus y square equal to a square? So if this is circle centered at the origin and this is x-axis, this is y-axis, this is x-axis, this is y-axis. If that is true, then if I take any point here that is x comma y, so if this has radius of 1, consider 1. From here to here, 1. Then from here to here, 1. Consider there is a point x comma y. Probably anything 0.5, 0.5, whatever. So if that is the case, then what is the radius? That is x square plus y square equal to a square. Then what we are trying to show is, what I am trying to say is, if radius is 1, then I cannot take any point x comma y any value. So if I take any x I can take, no one can stop me. So if this is x-axis, I take any x as 0.5, any x as 0.5, any y as 0.5, not possible. We cannot take both as whatever we want. So x as 0.5, y as 0.5, and I say there is a, consider there is a point x comma y is there, but this is 0.5, 0.5, where radius is 1, not possible. X is 0.5 whole square means 0.025, y square means 0.025, total addition is 0.5, that is not equal to radius square 1 square. So this proves that 1 is independent component x, any value I can take, but y is dependent upon x, whatever it is. So with that we calculated the gradient in, we remember that y equal to square root of 1 minus x square, a square minus x square. If x square plus y square equal to a square, this means that y equal to square root of a square minus x square. Dependent component, that is y, that is fx. So fx equal to square root of a square minus x square. That is f. If that is true, then what is dy by dx? Gradient or derivative, rate of derivative. If I have y and I calculate dy by dx, means y is collection and dy by dx is the rate of collection. So what is the gradient along x-axis? So dy by dx is that. So we calculated minus x by square root of a square minus x square I vector. If that is true, then dy by dx along x-axis that we have calculated. Now I have equation x square plus y square equal to a square. Okay. Now, now how we can represent in vector form? I can say that I have a point here that is x comma y. This is x-axis. This is y-axis. Can I take any point P here that is x comma y? I can take, but I am not. I am when radius is a, but I am not independent to set value for x and y. I can set value only for x that is less than equal to a. So x square plus y square equal to a square. If I put x equal to less than equal to a, then then y I can calculate whatever it is. But consider I have a point P at the circumference, any point P. If this is the point, if it is centered at the origin, from origin if I connect the P, then this is called position vector of the P, any point P. We are transforming the circle into vector. Now I have any point P can be considered as position vector P. If P is position vector at circumference curve, okay, the arc of the circle, then P, what is P? If this point is X and Y, if this is center, the line that connecting the X and Y from the center, what is P? P is nothing but we subtract the x to 0, y to 0, that is the vector. So that is nothing but x minus 0i plus y minus 0 j. So P point is xi plus yj. Now I transform the circle into vector form xi plus yj. Y is dependent upon x. Can I say that position vector at the circumference is xi plus a square root of a square minus x square j. This is now pure form in vector as far as circle is concerned. Now this P can be here, P can be here, P can be here, P can be here, P can be here. If that is the case, if this is the center, then P is rotating like, oh, I mean, I'm not that good in rotation. Okay, this is the beginning point and P is rotating like, okay, so P is rotating like this. If P is rotating like this, any moment if P is here, then this is the P vector. You can call it radial because it is along the radius. Now, if I have P equal to xi plus square root of a square minus x square j, where a is the radius of circle, if a is the if P equal to xi plus square root of a square minus x square j, if that is the if I'm sorry, P equal to xi plus a square root of a square minus x square j. If I say what is derivative of P? P, position vector. Calculus is science of algebra. Calculus is not science of vector form. That's why I say algebra. On top of algebra, one side is vector, another side is calculus. Calculus is tightly coupled with the algebra. So if I say dp by dx, how much position vector changes along x-axis? If there is a unit change along x-axis, if this is position vector, if this is position vector, this is x-axis, okay, position vector is xi plus yj. If I make unit change along x-axis, so if this is position vector and this is x-axis at point x, x comma y means x is down. This is x-axis, this is x-axis, but x is here. That's why this point is x comma y. If that is the case, then at this point, if I make one unit change, then how much this position vector would change? dp by dx. dp by dx. What differentiation says? If I have a function fx for which integration is gx, then for gx, differentiation is back to fx. If I have a gx, then I consider this is collection. If this is collection, then fx is rate of collection. So from rate of collection, if I do integration, then it becomes gx. If I do differentiation on the gx, then it becomes rate of collection. So if I have p equal to xi plus square root of a square minus x square j, and if I calculating dp by dx, this proves that p is nothing but net collection. So whatever the arc we have the length of the arc displacement. So we call it P as a position vector. We can call P as displacement vector because it is net collection. If I calculate the differentiation, we are moving toward velocity vector. So if Fx is velocity vector, then integration is displacement. If displacement is there, if gx is whatever I don't know, if I calculate the differentiation, at that moment it becomes collection. So like if I have acceleration, then integration is velocity. So velocity is net collection in this term. If I differentiate it, it becomes acceleration. If that is the case, then P here is considered as collection. If I do the differentiation, then we are moving towards velocity vector. Okay, so P equal to xi plus square root of a square minus x square j, where P is also considered as radial vector because it is along the radius. dp by dx, if I make unit change along x-axis when point along x-axis is x, how much P vector changes? Okay, how much p vector changes means what is p vector? What is vector? If I have vector xi plus square root of a square minus x square j, this proves that x is magnitude of vector xi. There are two vectors. This is addition. xi plus square root of a square minus x square j. There is addition in between. If there is addition, it between. And xi itself is a vector. Square root of a square minus x square j itself is a full-fledged vector. One is along x-axis, one is along y-axis. That is addition. Means I have many times I have demonstrated this. If consider this is origin and this is x-axis, this proves that there is a energy that is coming towards x-axis and the vector form, and its equation is xi. There is another energy that is moving towards from minus y direction going to origin, and then it is going towards y direction, and that vector is square root of a square minus x square j. So if this energy and this energy, if they meet at origin, then they will take one direction. So that is P xi one vector plus square root of a square minus x square j, another vector, they get added. If that is true, then if I do one unit of change in x, then how much p vector would change? Means how much I can see change, how much I can see change in both of the vector, both of the energy that are combining at origin. So if I make a small change in x, then both energy source that they are combining at origin, there will be change will be seen, not in the direction, in their magnitude. That is we are trying to calculate now. So two vector, they are joining at origin and becoming one vector, that is xi plus square root of a square minus x square j. Then xi one vector, square root of a square minus x square j another vector. If I differentiate dp by dx, then there is one unit change in x will bring how many unit of change in the magnitude of xi vector and square root of a square minus x square j vector, because at the end they will be in that direction only. Magnitude, how much accumulate in kind of you can say that in combination way, how much it would change. dp by dx equal to I minus x by square root of a square minus x square j. So this is the dp by dx. This is called velocity vector. What is I? What is I minus x by square root of a square minus x square j? dp by dx and p vector. Let's do dot product of these two vectors. Let's do dot product of these two vectors. So p vector and dp by dx vector, let's do dot product. So xi plus square root of a square minus x square j, one, and another is I minus x by square root of a square minus x square. So one will become x and another would become minus x, dot product. Then it will become 0. This proves that p vector and dp by dx vector, one is displacement vector and velocity vector, they are orthogonal to each other. They are orthogonal to each other. This proves that if this is p vector, then dp by dx vector is this. If this is p vector, then dp by dx vector is, that's why it is perpendicular. If this is p vector, then dp by dx is this. If this is p vector, then dp by dx is this. If this is p vector, then dp by dx is this. Everywhere it is perpendicular to the radius. If it is perpendicular, let's say, then this is moving along the curve. Can you see this? If that is true, then curve at any point, if I take curve at any point which is represented by velocity vector, is perpendicular to the radius. So actually we started discussion with the, can we calculate the derivative of sine x through trigonometry, not through the first principle, that is gx plus delta x minus gx divided by delta x. So when we took the trigonometry, at that time we made a hypothesis that the arc at any point x and y, that arc we are taking is perpendicular to the radius. So many ways we are proving it, that arc at any point it is perpendicular. So first we saw that if I have y equal to square root of a square minus x square, then the gradient along x-axis minus x by square root of a square minus x square I. If that is the case, then gradient is nothing but, it's a, if 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 x equal to 1, then it is infinite I. Means infinite I means it is I. Infinite I means the radius at x equal to a. X equal to a, the gradient is along the x-axis. So this is like radius. At this moment, we calculated dx by dy, not dy by d, dx by dy. Okay, and when I set it to 0, then y becomes 0. So when y is 0 on x-axis, then the slope of rate of change along the y-axis is nothing. This proves that at this point dx by dy 0 means there is a rate of change, there is a rate of change, at this point there is no rate of change. At this point, the arc is exactly parallel to y-axis. If arc is exactly parallel to y-axis, and at that moment the radius is along x-axis, means arc is perpendicular to the radius. This is second proof. First proof and second proof now we are giving through vector. Now we can go ahead and we can do computation on the vector through the polar coordinate systems also. So when we calculate through the polar coordinate system for the vector, calculate through the polar coordinate system to the vector, then what is the representation of any point P through polar coordinate system? So in polar coordinate system, x-axis is considered as a cos theta, y-axis is a sine theta, where a is the radius and theta is the angle. So if this is the x-axis and I make, if this is x-axis, if this is x-axis and then I make angle theta from x-axis and this is the radius and this is point P, then this point P, the angle theta, P radius A cos theta is x-axis and A sine theta is y-axis. If that is true, then position vector P is, now earlier it was xi plus yj, now it is x cos theta I plus A sine theta j. Now let's calculate dp by d theta. dp by d theta. Then it becomes minus A sine theta I plus A cos theta j. Let's do dot product of P and dp by d theta. Then it becomes cos theta minus sine theta, cos theta minus sine theta, cos theta minus sine theta plus sine theta cos theta becomes 0 again. If that is true, then the position vector and velocity vector, that is dp by d theta, are again perpendicular to each other. So position vector, if they are perpendicular to each other and dp by d theta is velocity vector, then if this is the radius, that is the position vector, then this is the perpendicular. So every moment it is along if it is perpendicular, then it is along the arc dp by dx at any point x comma y. If this is the position vector, then at any point x comma y, the velocity vector is perpendicular to the position vector. Okay, and this is how it is, the velocity vector, this is how it is moving. So it is representing the arc, whereas this is how the position vector is moving. Position vector is moving like this, then velocity vector is moving like this. Can I calculate again one more derivative of the dp by d theta, d2p by d theta square. Again one more derivative, acceleration vector. So now we have minus sine theta I, a minus sine theta I plus a cos theta j. Let's consider a as 1 only. So minus sine theta I plus cos theta j. If I do derivative again, then it becomes minus cos theta I and then minus sine theta j. So we had position vector cos theta I plus sine theta j and we have acceleration vector as minus cos theta I minus sin theta j. Certainly position vector and acceleration vector dot product is not zero. But again, velocity vector and acceleration vector dot product is zero. So position vector and acceleration vector, they are along the same line, but since it is negative, it is in opposite direction. So if this is the position vector that is moving in this direction, then this is again acceleration vector but moving towards the origin. If it is moving towards the origin, then it is acceleration vector, and from origin, if it is moving outwards from the circle, then it is position vector. So if you make derivative, then it is shifting by 90 degrees. So phase difference that we see after derivative is 90 degrees. So derivation is not only the magnitude, derivation also it is in direction also. This is what we are saying. So vector, we can say that it is it is a complete algebra. If algebra do not have direction, then vector is complete algebra in a sense that it has direction. So if I have a algebraic equation and then if I attach vector to it, then algebraic equation starts shining in a way that it gets direction also. Because algebraic equation has magnitude only with the variable, but vector has magnitude and direction. So if I go and keep calculating the derivative, if I go ahead and keep calculating the derivative, then derivative, derivative by derivative, then we are shifting the phase angle by 90 degree, 90 degree, 90 degree, 90 degree. What about if I have a vector? If I have a vector that is xi, xi, xi plus 2xj, xi plus 2xj, or xi plus xj, that is a vector. So if this is the line x-axis and this is y-axis, when x is 2, then it is 2i plus 2j. When x is 4, it is 4i plus 4j. This proves that vector is exactly at 45 degrees. Now let's calculate the derivative. So xi plus xj, that becomes I plus j. If it is I plus j, then it is 1 and 1. Same thing. This proves that derivative of a straight line do not change its derivative of a vector that is a straight line. Derivative of a vector that is a straight line, then its derivative is also in the same direction. If it is xi plus yj, xi plus yj, what is dot product of xi plus yj and I plus j? Then it is x plus x. It's not 0. So they are not perpendicular to each other. Let's consider a line equation x plus y equal to 1. I mean, no one can stop us doing the experiments, right? It is in our hand. No one is scolding us doing the experiment. So if I have x-axis and if I have y-axis, then x plus y equal to 1 is a line that intercepts x-axis and y-axis at point 1 comma 0 and 0 comma 1, because x plus y equal to 1. If x is 1, if x is 1, then y is 0. Whereas if x is 0, then y is 1. So this line is x plus y equal to 1, where this is x-axis and this is y-axis. It intercepts y-axis at 0 comma 1 and intercept x-axis at 1 comma 0. Let's calculate the partial derivative called gradient vector. Then gradient vector is I plus j. If this is the equation of line x plus y equal to 1, then let's differentiate it with x, then it becomes 1. Let's differentiate it with y, then it becomes 1. then the gradient vector is I plus j. If gradient vector is I plus j, then it is perpendicular. It is if this is x-axis, this is y-axis, and this is the line, then gradient vector is I plus j. This proves that even though it is a straight line in terms of line equation, then its gradient vector is perpendicular to it. This proves that the kind of the if that is true, then equation of line if I convert into vector form, then it is not straightforward. X plus y equal to 1, then x plus y coefficient is 1 1, then vector representation is I plus j. Not true. So vector representation of any straight line is its gradient vector, because if it is vector form, then derivation vector of a straight line, vector of a vector field, because it is algebraic vector, right? Xi plus yj is algebraic vector. So if I have a straight line algebraic vector, then its differentiation is also in the same direction. Whereas if I have a straight line as line equation, then its differentiation is perpendicular to it. It proves that the vector representation of a straight line is not straightforward. It is along its gradient vector. We will talk about it, that how, what is gradient vector in terms of in 3D equations. Like like I have a parabola. Okay, so I have a parabola and I have a sphere. I really have a sphere. This is a sphere. Okay, full fledged sphere. It's a tennis ball. And then I have a paraboloid. So if I cut it half, consider up till half only, then it is a paraboloid. It is a paraboloid. This is 3D. This is again, again 3D. So for the 3D shape, what is gradient vector? Then it will be more clear that what hidden thing we are doing in x plus y equal to 3 doesn't look like algebraic equation, right? Algebraic equation means you have independent and dependent components. Then only calculus identifies it. But x plus y equal to 1 doesn't look like an equation, right? If I say y equal to 1 minus x, then fx equal to 1 minus x. Then gradient vector dfx by dx along x-axis is minus I, minus I. It looks like a gradient vector. But x plus a calculating gradient, that's where books are not very good. This much clear distinction in gradient vector, you will not find even the best book in the world. All are mugging up here and there, copy and pasting. You must watch this channel, that how, what is gradient vector, I mean differential vector, differentiated vector, derivative vector, and then what is dimensionability. So what is algebra, what is calculus, what is vector, what is gradient vector, what is numeric science, and what is different coordinate system. So if I say x plus y equal to 1, then what is hidden behind it, and how we can say in terms of real algebra, where function fx and fxy, whatever it is, that comes into the picture. Okay, so we will see about it. So kind of it's getting elongated in this primitive calculus. I thought I could finish it today, honestly. So we will do it. So kind of, if I finish it by this, then we will talk about gradient vector in kind of calculus in more in-depth way. But we have done why calculus, how calculus. So how calculus propagates from polynomial to sinusoidal and top. So we proved it. So sin x equal to cos x. Differentiation of sin x is cos x through alternative way also, where arc, any point arc of the circle is perpendicular to the radius. So we will talk on gradient vector. I'll see if it is a uh, kind of stretching the series of the primitive calculus, or altogether it will be different series section that is gradient vector. So that we will see.